Good day. Today we start our lecture, which is lecture number 27, and this is the design of springs. Now, for the design of springs, we start with the how we define basically a spring. All of us know what is spring. We have used springs in everyday life. So, basically we can say that springs are used as a flexible joint between two parts or bodies. Now, here you are having some sort of objectives for the spring. What is that one? First of all, to cushion, absorb or control energy due to shock. This is a very common thing what we find out, the application of the springs in car springs or alloy buffers, and to control energy due to shock is a well known situations for the springs, supports and vibration dampers. Next, to control motion. What is this idea to control motion? Means maintaining contact between two elements as cam and its followers. You understand that when if you just think of the cam and follower arrangements widely used in so many applications, then you will be finding out a spring is there which always keeps the contacts between the cam and the followers, thus it controls the motion. Now, whenever you see someone driving a car, he uses a brake or a clutch for the car control of the car control as far as the motion is concerned, and there what you do, you apply a brake which again eventually is having a spring system, and the clutch is also having a spring system which engages and disengages aided with the mechanism of a system of springs or a single spring like that. And another one is the restoration of a machine part to its normal position when the applied force is withdrawn. A typical example, you know, that in turbines, in the turbines, suppose if we take an example, then what we see that whenever you are having to control the speed, okay, which is going on increasing or decreasing, a governor system is used which controls the motion or the rotation of the turbine wheels, and thus say the flow through the turbine vanes by the governor mechanism which controls a series of say vanes for inlet water impingement like that, and that is also controlled by springs. And here we use again as some sort of a control motion, and that is also using a spring governor. And another example, that some valves, actuator valves are also having the spring which can have some arrangements for the control motion. And the very common use of spring, you can see the measure to measure forces, that is the spring balances and gauges. What you utilize is a spring, and to store energy in clocks or the starters. However, we do not find much of the winding clocks nowadays, but still you must have seen the clocks, the spiral type of springs which first you wind it to coil and then gradually it recoils and to the stored energy is recoiled, and this phenomena also you can see in the toys used by the children. Now, in the lecture design of springs, we will consider two aspects. One is the design of helical springs, another is the design of leaf springs. These two springs are very widely used in actual practice or actual fields in so many cases, and some of the examples just now what I have cited. So, we start our lecture or with the design of helical springs. Here we start with the commonly used spring materials. One of the very important thing is the choice of the spring material, so that the purpose for which the spring is made is actually performed nicely. Now, in this case, normally if you are having the springs of very small diameter and the wear diameters are also small, then the springs are normally manufactured by a cold drawn process through a mandrel. However, for the very large springs having also large coil diameters and wear diameters, one has to go for manufacture by a hot processes, means after heating the wire and then using a proper mandrel to wind the coils. Now, coming back to our discussion on the spring materials, we see here that the common spring steel, which is called the hard drawn wire, is the cheapest among all, and it is normally used for low stress conditions and static loads. The material is not suitable for sub-zero temperatures or temperatures above 1 degree centigrade. This is a very common cheap type of springs what we can use in everyday life. Next comes the oil tempered wire. It is a cold drawn wire, but after that it is quenched, tempered, and it is again a general purpose steel. However, it is not suitable for fatigue or sudden loads, also at sub-zero temperatures and also at temperatures which are above 180 degree centigrade. When you go for very high stress conditions, then alloy steels, one of these is a chrome vanadium steel, is used. It can be used at a moderately higher temperature around 220 degrees Celsius, and this has got a very good fatigue resistance and long endurance for shock and impact loads. Another one is also the chrome silicon. This material also uses for highly stretched springs, and it offers an excellent service for long life, shock loading and temperatures relatively higher than chrome vanadium, that is around 250 degrees Celsius. So, these two type of steels are, as you can see, are used for the fatigue conditions. Music wire. This is the most used wire for small springs. It is the toughest and has the highest tensile strength and can withstand repeated loading at high stress values. However, it cannot be used at sub-zero temperatures or at temperatures above 180 degrees centigrade. But you see that normally when you talk about the springs, you will be finding out that music wire comes out a very common choice because of the reasons just stated. Now, other one is the phosphor bronze or spring brass. These are also quite used, and it has good corrosion resistance and electrical conductivity. That is the reason for the electrical contacts and other things you use this type of spring materials. Spring brass has a property that it can be used also at sub-zero temperatures. Now, there are several other spring materials like stainless steel also and some more alloying elements. However, in this particular one, the names of those materials are given which are very common in everyday practice. Now, Let us come down to the stresses what occur in helical spring. Now, to look at the helical spring situation, let us look at the figure first. This is a schematic representation of a spring. So, this is the coil cross sections. Okay. Now, these are the coil cross sections. So, if you look, this coil is actually wound in this fashion, and this bold one, what you can see, these are all outlines of the coil. Okay. These are the coil, this is going like this, another one is like this, so and so forth. Now, this is a cut section, means the end from the entire coil somewhere you make a cut, and as a reason it is given in a shaded way. Now, if you look at the free body diagram, then what we will be getting? We just concentrate on this particular zone. Then what you see is that if we look for this one, then obviously at a cut section you are having a vertical equilibrium will give you the force, the directly this force which is a shear force coming in this direction, and the cut section, the torque which will be coming over here is in this direction, and there is no horizontal force coming into picture because there is externally there is no horizontal force present. So, just from our fundamental ideas of the free body diagram, you can see that this is a situation any section of a spring is experiencing, that is simply a torque and a force. This is the shear force. Now, you know, whenever there is a shear force, you know that there will be an associated some amount of bending moment, but you do not see any bending moment over here. The reason, you just try to analyze yourself. The reason I am telling is because simply it is a curved one. As because it is a curved one, then that is a reason there is no bending moment appearing in the free body diagram of this particular cut section of a spring. Now, as we have learned earlier that the stresses that will be generated due to the torsion as well as the direct shear can be computed using the simple equations, and we can superimpose the stresses that is occurring due to the torsion and direct shear, and thus we will be getting the final expression. I have written here the final expression as tau max as Ks 8fd pi d cube. Let us see that how we get this simple relationship. Now, as we have seen, I am not drawing the entire one, entire picture I am not drawing, just look into this one. So, if we have a cut section and we are having an torsion T and a direct shear F that is acting into this direction. So, what is the shear stress due to torsion? Tau T, that we know from our fundamental ideas, that T R by I P. We know all the notations, okay, the standard notations we are using. What is the torque that is acting here, that we have seen from the free body diagram? This is the F, and this happens to be the radius of the coil, or the total one. Well, just one second. It is better that I give the notation as is given in the earlier figure. So, this distance comes out to be d by 2. So, if we replace one after other, then what you get? You get T this T, magnitude of T comes out to be F into d by 2. What is coming out to be this small r? Small r means here, from here it is a small r. So, at this location we are giving it is as d by 2, okay, where d stands for the diameter of the coil. This has got the diameter, I am sorry, diameter of the coil wire divided by IP. So, that gives you the pi d to the power 4 by 32. So, if we simplify, then what comes out to be 8 f d by pi d cube. The force due to tau direct, how you get it? This tau direct will be coming out to be the total load by area. So, total load is F and this comes out to be pi by 4 d square. So, that means it comes out to be equals to, just one second, (4f) by pi d square. So, we get one stress due to the direct one and another one we are getting due to the torsion one. So, what is the net stress that is acting onto the spring at any point? It will be the summation of this one and this one. Now, one thing I just would like to mention here, see, we have taken the average stress, although we know that there is an distribution of the stress, direct shear stress, but here we have taken just as an average stress. So, if we try to put another notation as tau max, then what we note down? We note down that it should be the summation of tau t and tau d, but at the point where it should show up the maximum. If we look into this one, then you can see that at this location the direction of this is the direction of the tau t, this tau t. So, if I just give another one, just one second, if I give this as tau t, this as tau direct, d stands for tau direct, then here we are getting an summation effect. However, if you look into this one, you can see the shear stress will be here and here, this is tau t and this is tau d. So, it is a minus of this one. So, you take this one minus that one will give you the value. So, obviously, when we consider the value tau max, then we find that it will be the summation of tau t plus tau t, and this comes out to be the tau max maximum. Means tau max means it represents a maximum shear stress that is occurring, and you can see this maximum shear stress is occurring if we look to this particular spring as a whole. I am just giving you the idea just here once again. Okay. So, if you look to this one, that means a series of springs like that, what we have drawn earlier, like, okay. So, what it is giving, this is a spring acted upon by the force F. At this zone we are always getting, similarly if you look at this one, we will be always getting at the inner side. So, the inner side, this is the inner side of the spring which always gets heavily loaded. So, the spring failure is expected always to have from the inner side of the spring, and that actually really happens. Now, you might be questioning that I have taken an example where the spring is in tensile mode. That means, you are actually pulling the spring. If this is a spring, then you are pulling the spring like this. So, this is what you are getting the spring. Now, what I mean to say is that had the spring was in compressive mode, then and then also you see the inner side of the spring. So, that means, if you make a cut section here, just to cut, then you draw the cut section, then what will happen to the free body diagram? Load will go like this one, and the torque from the free body diagram will be like this. See, again you will be finding out this inner side is mostly stressed. That means, what is the idea I am just trying to define you, I mean explain you, is that irrespective of a spring being in compressive mode or in a tensile mode, you will be always finding that maximum shear stress is occurring at the inner side of the spring. So, thereby the chances of failure or the failure starts always from the inner side. Coming back to this equation, what we have derived, tau max equals to tau t plus tau d. If we look into the entire form, then what we have seen, that we have seen like this, that tau max comes out to be how much? 8 f d plus pi d cube plus 4 f by pi d square. Is it all right? So, 8 f d by pi d cube plus 4 f d 4 f plus pi d square. So, this one, if we take common 8 f d by pi d cube, what we get? 1 plus, what is this thing coming out to be? 1 plus 1 by 2 into capital D by small d. That is what you will be getting over here. Now, this one, I suppose I am correct. If you take is common, that means this is 8, means you divide by 2. So, if you are taking common d, so d comes at the bottom and 1 d comes at the top, which comes over here. Well, so if it is like this, then we represent it normally. I am just, without writing, I am just erasing this portion. Okay, we write down this normally by an word 2 multiplied by capital C. So, what do you get? That C stands for capital D by small d, and this has got a name called spring index. Okay. Now, we can see that higher the value of the C, lower the effect of this 1 by 2 will come into picture. The mostly predominantly it will be coming as the torsional stress. Now, this one, including this particular one, is again this entire situation, means what I mean to say, this entire group of 1 plus 1 by 2 C is written as a value K s. So, thereby we get an expression like K s into 8 f d by pi d cube as a tau max occurring into a spring. So, let us go down to the earlier slide. So, you can see. So, this is what it has been written, that tau max equals to K s by 8 f d by pi d cube, where this K s is called shear stress correction factor, and as I told you that K s is given by the expression 1 plus 1 by 2 c, and where c is a d by d, that is called the spring index. So, this is the equation for the maximum shear stress occurring in a spring. However, this particular one, this expression is sometimes again written as in the form Kw 8 f d pi d cube. We can see we have replaced the Ks by Kw. What is this one? Here this Kw is the wall correction factor, and named after a researcher who did a lot of work on the spring, A.M. Wall, and that is a wall correction factor, and this correction factor is given by this expression 4 c minus 1 by 4 c minus 4 plus 0.615 by c. Now, this is what you just see the heading, the stresses in the helical spring with curvature effect. As a matter of fact, it should be like this, that means this particular Kw or the wall correction factor includes both the curvature effect and the shear stress correction factor together. So, I mean what is the idea of Kw? Kw or the total K, if we consider this wall correction factor, then it contains what I was just telling, that the curvature effect as well as the direct shear effect. Now, one should know that I am telling every time curvature effect. What is basically a curvature effect? See, this way we can define a curvature effect or try to explain a curvature effect. See, if we look spring, one small section. Okay. So, it is basically circular. So, this is the center of the spring, and the load as we have drawn, suppose it is you are just pulling from the center. This is one spring what you have just cut out and just represented. Now, suppose we just hold this section and you just give a rotation, all right, you give a rotation. I think if we look from this side, the rotation conforms with the direction what we have just given in the earlier slide. So, if you give a rotation, then what will happen? With respect to this face, there will be a rotation of this face. Now, suppose we point out this one A and B, and this is C and D. Well, with respect to this one, if we rotate, then the point B will be rotating with respect to what we just trying to say at the very beginning. Suppose just turn view something like that, C and C point is there. So, after rotation, suppose the D has come down over here, this is the point D, and this was A, and this B has come down over here. Okay. So, we can see the rotation for this two, the top face point D with respect to C, and in the down face B with respect to A is having the same thing, because that is the assumption while we have taken up, you remember, in doing the simple torsion problems. However, you see the length of the fiber, this length of the fiber is smaller compared to this length of the fiber. So, what will be the shearing strain? The shearing strain will be more. So, here we understand this, if we write this as an shearing strain, this location will be what? More, and at this location it will be less. That means, here that is the what we consider as an curvature effect. Now, you understand that what will be happening. Suppose we are having a small spring, okay, of the same diameter of the wire, then you can see onto this zone the curvature effect is more. Of the same wire, if we make a large one, okay, then you can see for the same thing, if we extend it, this curvature effect will be less. So, obviously, that means what is happening? The ratio of D, that means C equals to what is this D by D. The more and more the spring index, the more and more the spring index, then what will be having? The lesser the curvature effect. So, normally for the heavy coils, well, one of the examples, that means if you see that train coaches, then when the suspensions which uses helical springs in the railway carriages, you will be seeing that it is made of a very large diameter wire. Relatively the coil diameters are small. So, in those cases what will happen? These curvature factors will be predominantly high. So, that is what we understand by the curvature effect. However, as I told you that the effect of curvature and the effect of direct shear together, you get this value of Kw. So, it is customary that instead of writing Ks into 8 Fd by pi d cube, we will write down this Ks as Kw, so that the effect of curvature is taken into consideration. So, this is the basic equation what we use for the stresses arising in a helical spring, whether it is in compression mode or it is in tensile mode. So, once we have learned this one, then let us try to find out what is the deflection of a helical spring. Now, in the same manner, you can see we have taken up a schematic view of the spring. So, these are the spring coils. Okay. I hope you are the same figure, and this is the cross section of the cut, and it is acted upon by the same force downward, means that spring is in tensile in nature. Now, while we compute the deflection of helical spring, just by simple geometry we can find out that the deflection of a helical spring will be given by this particular formula, this 8 f dq by n divided by g d to the power 4, where n is the number of active coils. Now, again the question comes, what is the word active means? Basically, you know, we will be dealing with this particular term active coil after just after these lectures or these discussions. But still, just to give an idea, suppose this spring, the F cannot just hang on to the space, it has to have some material contact. Suppose it is a spring, then normally you will see a spring something like this. A spring will have okay, and then your hook. So, that means these hooks where you have to put these loads. Now, these sort of situations, okay, just that means putting an hook etc., these are although a part of a spring, but it do not contribute actually to the spring deflection of spring stresses. It has to be taken care of in a different manner. So, suppose we consider that this is the zone, this is a zone normally where we are having all the coils which contribute to the deflections of the stresses, then these many coils are what we mean by the active coils. Well, now the G I need not explain once again, you know that G is a shear modulus of elasticity. How we actually try to find out this deflection of an helical spring from the geometry? You see, just a situation before the application of the F, what is happening? We have taken and cut and we arbitrarily draw a line from this point to this point, and let us denote that the length of this line is L, okay, some length L of this line. You apply the force F here and also somewhere in the down, and what you will be getting? That means the spring will just extend, and what will happen to this face? You see from the earlier free body diagram that it will experience a torque like that. So, if it is experiencing a torque like that, means with respect to just the earlier section, you understand what I mean to the just earlier section, means I am just trying to put it like this. Okay. Now, this is the coil, means it is an enter coil, and this is the face what we are considering here. That means, this is the face F and this is the face F. So, with respect to the center, if we draw two faces, then this is a situation, all right. And now let us consider this angle to be something like say beta. So, here this angle, well, we take a very small angle as a matter of fact, okay, it will be better. Just let us take a very small angle and write down this angle to be something like d beta. Okay, this is the angle. Then let us imagine that with respect to this small length segment, all other means all other springs are somewhat rigid, means all these springs are rigid, only onto the entire spring you are having a rotation with of this face with respect to this, only we are considering this small length of the spring to be active one, means actually responding to the torsional force, and that is actually rotating. All other spring coils, means entire spring coils that you are having, everything is rigid, only that small portion is active where you can have a rotation like this. So, from this particular rotation, if we come down to this particular figure, then what will happen? The length L, just due to the rotation like that, this line L will travel somewhere over here. This is the line, it will come over here. Now, what you are getting? That this line has come over here, and this angle, let us call this angle as a small angle d phi. Then what is the deflection? See, this has come over here. So, if we consider just an horizontal line through this one, then this distance is delta. delta, well, I should not put it delta, say it is coming out to be d delta. Will it be all right? I think because it is on a small elemental length. So, let us put this one as a d delta. That means, what is this d delta? This d delta has come up due to the rotation of this face or this face with respect to another face which is very close to this one, only subtending a small angle delta beta. So, we know that to find out the deflection of the helical spring, we have to find out this value of the small displacement that is created due to the rotation of a segment of a small segment of the spring. So, that means we have to compute the d delta, and then if we can compute d delta, then immediately we can compute the delta considering the effect of all other coils for the entire spring. So, how we can take up? We can take up in this situation. Let us come down over here, just have an idea. We know if we concentrate on this particular figure, this is a central line. The line was like this, it was L, it came down over here, then you are having, so this is coming over here, well this is the line. So, you get a line like this, and we are interested to find out this component. This is the portion we would like to find out. How we can find out this line? Suppose this angle, this particular angle, let us say d gamma. What is this line? Then we can see this d delta equals to, this is the thing, and what is this length? We had denoted this angle as delta phi. So, it is, this length is L d phi. So, this one by this one is this sine of this angle, that means it is coming out to be L d phi sine d gamma, and that comes out to be L d phi sine d gamma. What we can find out? This sine d, this is the same thing, and if you consider how much this is, d by 2. So, that comes out to be into d by 2 divided by L. So, that is a sine gamma. So, this comes out to be d phi into d by 2. What is basically we want to find out is the value of d phi. How we can get the value of d phi? Let us go down to the basic concept of the phi. We know it was T L by G I P. Okay, that was the fundamental equation for the shaft rotation. We did it earlier. So, taking the help of this equation, we find out that the small angle d phi will be created by what? Torque as usual, F into d by 2 and multiplied by L. What is this L? You remember that we consider this as the segment, a spring segment of this length. Okay. So, this was angle d beta. What is this one? So, this L, or here L will be replaced by a dl, the small elemental length, and this length we can find out in which way. This distance is d by 2 and this is r d theta, means d by 2 into delta beta. This is this length. All right. So, you substitute this one with d by 2 into delta beta g, what is the value of I p, pi d to the power 4 by 32. So, oh please excuse me, I have just drawn the internal, this is a d phi. G into pi d to the power 4 by 32. Let us simplify this expression, then we get this value of d phi, and that comes out to be equals to 8 into f d square delta beta by g pi d to the power 4. This value again we substitute over here. Okay. So, if we substitute here, then what we get? We will be getting an expression. I think this is no more required, we can erase this portion. Okay. So, this one d delta comes out to be how much? We are substituting this one. So, 2 cancels. So, 4 f what d cube d into dt cube delta beta by g pi d to the power 4. All right. So, what we will be getting? The value of delta integral 0 to, this was only for a small segment of the coil, and now we integrate for the entire 2 pi is one coil and number of coils for entire angle. This is a delta beta angle. So, we go by 1 is 2 pi, we go by number of coils and it is 2 pi n. So, if we integrate it is, and it is coming out to be 4 f d cube d beta divided by g pi d to the power 4. That comes out to be how much? 2 into pi and pi will cancel out. So, this delta beta will be simply beta and this 2 pi n will be substituted. So, you understand this will be coming out to be 2 8 f d cube remaining as it is, 2 pi n, this pi cancels, n remains, 2 gets multiplied by 4 with 8. So, this is n divided by g d to the power 4. So, you can see, so we go down to this one, and in that precisely we see that delta equals to delta equals to 8 f d cube into number of active coils divided by g d to the power 4. So, we find a very simple relationship to find out the deflection of the helical spring. Now, basically what we require in this case, the stresses that is arising into the coil, so that you can take the proper material or the dimensions of the coil, and where the spring parameters are its length, its diameter of the wire, diameter of the coil, and the desired deflection what is coming into picture. So, this will give you the total deflection of helical spring as well as the stresses. So, this once we find out, then we can have the design conditions. Now, let us go to another aspects of the spring design, which is coming out to be the design of helical springs for variable load. Now, normally what we have seen, the stresses what is coming into picture and the deflections, everything is just what we calculated right now will be mostly meant for the static loading conditions. Well, the basic stress equations remain same. However, the deflection of the spring is universal. It can be for variable load or the static load, does not matter, but anyway the stresses what we have derived that equation is a condition where the loads are static in nature. But as a matter of fact, you know that spring applications comes heavily in the conditions where the loads are not a static loading or a constant loading, but it is a variable load. Say as for a car, for example, you will be having the rear suspensions of the modern cars which has normally a coiled springs will be always subjected to a fluctuating load depending upon the road conditions. It could go very severe also. So, we have to modify the concept of the design or the concept of analysis of stress onto the coil that is coming due to such type of variable loading. Well, you see one of the figures what is represented over here is something like this, and you see this is called the repeated stress, and this is a total stress and time. You can see one important feature is that the stress is actually going in this manner. The stress is going to some maximum value and then it is coming down to a 0 value. That means this tau mean is 0. Here once we call about the load, we understand that this load is causing a shear stress in the spring, because primarily the springs will be subjected to shear stresses only. So, what you can see is that the stress which is coming up, that is a tau max and the tau mean, which essentially comes out to be 0, and this we call as an repeated stress. So, obviously we know from our earlier lesson what is this one. This is called a stress amplitude and this is called the mean stress or the average stress, whatever may be. So, in this case you can see the because the tau minimum is 0. So, this particular mean stress is same as this particular stress amplitude, and which is nothing but the tau max divided by 2, means half of the maximum stress that is occurring in the spring. What for? This figure has been given. This figure has a significance. See, whenever we talked about the variable load design in the earlier lecture, then you remember that one of the situation which is important is the material property, and in that time whenever we consider a variable load design, in addition to the material properties like yield point and ultimate strength, we require another material property that is called endurance limit. That means the value of the material when it is undergoing a variable load or a fatigue situation, we consider a endurance limit. I do not elaborate on the endurance limit because already we have done a lot on the endurance limit. Now, normally at that particular situation, you have seen that the endurance limit of a material was obtained by a cyclic loading situation. That means, a specimen was repeatedly loaded for complete reversal of the stresses. That means, a specimen was rotating, having an concentrated load at the middle, that gave rise to a continuous stress repetitions of cyclic in nature, means completely reversed nature. In the same manner, when we consider the design of a spring, then we know that spring is primarily acted upon by what? The shear stresses. So, in case of variable load design condition, what material property we require? We require an endurance limit of the spring material when it is undergoing a pulsating type of shear loading situation. In that case, what is being done? That if we just can visualize the experiment like this. Suppose it is a torsion bar, then what we are considering? That we are considering the torsion bar to be loaded to the maximum and 0, loaded to the maximum and then we get 0. Okay? So, that is what is being done in the case of the material testing. Why such situation comes into picture? Because if you consider a case of compressive spring or a tensile spring, then the situation is like that. Say for an example, first let us consider a compression spring. What will happen a compression spring in actual operation? That if a compression spring is there in between this two plates, then it will go down to the maximum, then come down to the 0. You cannot go onto the reverse direction, because then the spring will get loosen in contact and it will just fall out. So, what will happen? The spring will at the most will be compressed totally to a maximum limit, then come down to 0. 0 is the limit, beyond which if it goes like that, then the spring will just fall from its seat. So, that is the reason what is happening. The maximum what you can attain in case of the compressive spring is maximum load to 0 load. So, that is the reason we consider a typical experiment of that nature. So, what we see that in the next class we will continue our discussion, which is very interesting for the design of the springs when it is subjected to a variable load. Thank you.